She was one of the foremost experts on toxic metals in the United States. She wore her gloves. She worked under a ventilation hood. She followed every safety rule her field had established. And she was dying of mercury poisoning anyway, because nobody yet knew those rules were not enough. Karen Wetterhahn was a professor of chemistry at Dartmouth College in Hanover, New Hampshire. She had earned her doctorate from Columbia University in 1975, joined Dartmouth's faculty the following year, and by the mid-1990s had published more than 85 research papers. Her specialty was precisely the thing that would eventually kill her: toxic metal exposure, how heavy metals enter the body, how they damage cells, and how the body tries to repair itself. Beyond her research, she had helped found Dartmouth's Women in Science project in 1990, a program that raised the proportion of women science majors at the college from 13 to 25%. She was not a junior researcher making a rookie mistake. She was the person other researchers consulted when they needed to understand how poisons behave. On August 14, 1996, Wetterhahn was working in her laboratory. Her research at that moment involved studying how mercury ions interact with DNA repair proteins, the cellular machinery that fixes damage to genetic material. And she was also investigating the toxic properties of cadmium, another heavy metal. For one part of this work, she was using a compound called dimethylmercury, an organomercury substance that served as the standard internal reference for a specific type of laboratory measurement called nuclear magnetic resonance spectroscopy, a technique used to precisely characterize mercury-containing compounds. While transferring the dimethylmercury using a pipette, she spilled several drops onto her latex-gloved hand. She did not believe she was in immediate danger. She was wearing the gloves that laboratory protocol required. She cleaned up the area carefully before removing her protective equipment. Nothing in her training, nothing in the published safety literature at that time, told her she had just received a lethal exposure. Approximately 3 months later, in November 1996, she began experiencing brief episodes of abdominal discomfort and noticed significant weight loss. These symptoms are non-specific, and at that stage, there was no immediate reason to connect them to a laboratory incident that had seemed entirely routine. Then, in January 1997, 5 months after the spill, the neurological symptoms arrived: loss of balance, slurred speech. These are the more characteristic signs of mercury poisoning: damage to the nervous system that manifests as the brain's fine motor coordination beginning to fail. At this point, testing confirmed what was happening. Her blood mercury level was measured at 4,000 micrograms per liter. The toxic threshold is 200 micrograms per liter. The normal range is between 1 and 8. Her reading was 20 times the toxic threshold. Her urinary mercury was similarly extreme, at 234 micrograms per liter against a toxic threshold of 50. These numbers described a nervous system that had been absorbing a powerful neurotoxin for months. Doctors initiated aggressive chelation therapy, a treatment that uses chemical agents to bind to heavy metals in the body so they can be excreted. But the window for intervention had already closed. Within 3 weeks of the neurological symptoms appearing, Wetterhahn lapsed into what appeared to be a vegetative state. One of her former students described a moment when her husband observed tears on her face and asked the doctors whether she was in pain. The doctors responded that it did not appear her brain could even register pain. She was removed from life support and died on June 8, 1997. She was 48 years old. It had been 10 months since the spill. The finding that redirected the entire case came from her colleagues' investigation afterward. They tested dimethylmercury against the standard latex gloves Wetterhahn had been wearing and found that the compound permeated the glove material and reached the skin within approximately 15 seconds. The molecule is small and non-polar, chemically neutral in a way that allows it to slip through the latex barrier as if it barely existed. The gloves that were considered adequate protection were, for this particular compound, essentially no protection at all. The question the medical investigation had to answer was, why did dimethylmercury prove so catastrophically more dangerous than other mercury compounds, and why did the exposure remain invisible for so long before producing devastating neurological damage? Mercury exists in several chemical forms, and they do not behave identically in the body. Elemental mercury, the liquid metal, is absorbed slowly through the lungs. Inorganic mercury salts can be toxic when ingested, but are not efficiently absorbed through skin. Organic mercury compounds are a different matter entirely. The most dangerous of these are the alkyl mercury compounds, and dimethylmercury sits at the extreme end of that category. Because dimethylmercury is both small and chemically non-polar, it crosses biological membranes with unusual ease. It passes through the skin. It passes through the blood-brain barrier, the protective filtering system that normally shields brain tissue from many circulating toxins. Once inside the nervous system, organic mercury disrupts the function of neurons, the cells that carry electrical signals. It interferes with cellular processes at a fundamental level, causing damage that accumulates over time and, beyond a certain threshold, cannot be reversed. The long latency between exposure and severe symptoms is itself part of the danger. The compound was distributing through her nervous system while she felt only vague abdominal discomfort. Her hair analysis showed a dramatic spike in mercury levels beginning 17 days after the exposure, peaking at 39 days, then gradually declining as the compound redistributed from blood into tissue. That redistribution was not a sign of recovery. It was mercury moving deeper into the body. The chelation therapy that was attempted works by binding to mercury molecules in the bloodstream, allowing them to be filtered out through the kidneys. For it to be effective, mercury must still be circulating. By the time Wetterhahn's exposure was identified and treatment began, the compound had already deposited extensively in her brain tissue, where chelation agents have limited reach. The treatment was not able to reverse the damage already done. What this case established is specific and consequential. Wetterhahn's death demonstrated that a compound classified as acutely hazardous could, under real working conditions, defeat the protective equipment that safety standards at the time mandated. Every precaution she took was the correct precaution according to the standards of 1996. The standards were wrong about this compound. Following her death, the Occupational Safety and Health Administration issued guidance recommending that dimethylmercury be avoided unless absolutely necessary and requiring laminate gloves when the compound must be handled. Her case also prompted consideration of replacing dimethylmercury as the standard reference material for mercury spectroscopy entirely, so that researchers would not need to work with it at all. What cannot be generalized from this case is the level of risk attached to mercury in other forms, to other laboratory chemicals, or to routine occupational exposure. Dimethylmercury is among the most acutely toxic substances used in research settings, and the failure mode that killed Wetterhahn was specific to its unusual ability to cross both latex barriers and the blood-brain barrier. Her case does not describe what happens with most laboratory incidents. It describes what happens at the extreme end, when a safety system has a gap nobody has yet measured. The opening image returns here, an expert, fully protected by every standard her field had established, harmed by the very substance she studied. The contradiction was not carelessness. It was an unmeasured gap between assumed safety and actual safety, a gap that existed not because the precautions were ignored, but because no one had yet tested whether they worked for this particular compound under realistic conditions. Her colleagues tested the gloves only after she became ill. The data that could have protected her did not exist until her case created the need to look. Karen Wetterhahn's death changed laboratory safety standards in ways that continue to protect researchers today. The Women in Science project she founded remains a national model. The gap she inadvertently exposed is now, because of her case, a gap that is known and addressed. This video is based on a publicly documented medical case and is intended for education and storytelling only. It is not medical advice. If you are experiencing concerning symptoms, consult a licensed medical professional. Medical mysteries. Every symptom has a story. Every patient deserves to be heard. Medical disclaimer. This video is based on real, publicly documented medical case reports and is intended for educational and storytelling purposes only. It is not medical advice. If you or someone you know is experiencing similar symptoms, please consult a licensed physician immediately.